All right, so now we'll try the buffer overflow leading to command injection. And here we get into proper C memory corruption, although this is the simplest case. So here I have a C program, and it defines a main program where it reads in two variables, your name, it reads your name, and then it calls a function which has two string variables, and the second one is always date. And in the subroutine, it copies them into smaller variables that only have room for 40 characters, smaller than your name. And then it first says goodbye name, and then it executes the command in the second variable. All right, and that does that with the system command here. And the point of this is the two variables are stored in memory, and you can exceed the memory reserved for the name and wander into the memory reserved for the command. So this is the simplest kind of buffer overflow where you do not hit control structures like the return pointer. Instead, you just corrupt the value of a second variable. And so I've got one of these live on the web here. So if I put in a name of AA and execute it, it just says, you sent AA, it became AA, executing command. Right, so here's what it does. It prints the name, and it prints executing command uname -a, and then it executes that command. So this just has a generic harmless Unix command that it executes. And for your information, it shows where they're stored. So the name is here at location BD0, but the command is at BF8. So that is 40 characters passed in base 16. So if you put in 40 characters here, followed by LS, then it has this result. It says your name is all 42 characters because in C, the string length is not stored anywhere, and it just reads the string until it finds a null character. So if I put in too much length, it will just regard it as a valid string, but these LS actually leaked into the other variable, so now the command turned into LS. So again, I can now execute arbitrary code. I can put LS semicolon who am I, semicolon date, and it will execute that. So here's the results of LS. Here's the results of who am I. Here's date. And again, there are some flags to find on the server. So this is a command injection in C, and that's the simplest case. But the most important case is this one, the classic Aleph null type buffer overflow. So let me make this one. If I can make it live and we can see it. So this is pwd.c. All right. Let me get out of here. Let's make a directory. All right. Oops. All right. So what I've got here, escape Y to get rid of the colors. Okay, what I've got here is a main program that calls some subroutine, and then if that returns 1, it will print fail, otherwise you'll win. So the test, it has room for a 10-character password. It reads that from the user, but it allows you to put in up to 50 characters, and then it returns. It always returns 1, so you always fail. You'll never make it to this win function, and that's our goal. So let's see if I have the necessary libraries to compile this as 32-bit on here. Oh, good, right there it is. So this will either work or it won't. I might have to install a library. Yes, and I thought I had it in this project. Just a moment. I think it's where you set up your Debian machine up here. See, I might have to go look it up, but all right. All right, install your it's 32-bit GCC compile 32-bit code on Debian. Should have been in my project. Somehow this version of my project doesn't have it right there where it needs to be. There. All right. There it is, GCT multi-lib. All right, that's the command. All right, let's try that. That looks better. All right, now I can compile the code. Okay, so that's the missing command, and I'm just going to throw that here so I remember to put that in the project. There we go. All right, so now I've got 32-bit code. And you can do 64-bit code too, but I wanted to start with 32-bit because it's simpler. So if I do file on my compiled program, it tells you this is a 32-bit executable, which is what I expect. So I can run this, and it asks me for a password, and if I give it a password, it prints fail. There is no correct password. Whatever I give it, it's going to fail. But if I give it a longer password, like this one here, it's going to give me a segmentation fault. And that is the clue that I have a memory corruption vulnerability. I was able to trick it into trying to use an invalid memory address, which means that some portion of this input was copied and used as an address instead of just being an input string the way it should have been. All right, so to make life easy, I'm going to turn off address space layout randomization, which makes this exploit more difficult, and we don't need that right now. So let's just turn that off. It's not listening to me. All right. Right-click, copy, right-click, Control-V. There we go. All right, so I execute elevate to administrator. I turn off this randomized VA space, and now we're fine. So now I can, let's get rid of this. All right, now I can run this program and give it a password of 1, and notice it prints the address. The address is 616, and if I run it again, the address is now always the same. This is what I want. I want it to not be moving around in memory, but to have a fixed address. That's going to make it possible for us to attack it in a simple way. And the way to see what's going on is to use the GNU debugger. So I run it in a debugger in quiet mode just to avoid having a big ugly banner. And now I can list the source code. And I can work from C source code, which is very handy. So what happens in this program, let me make that bigger. All right. So what happens is it calls this test PW program. Here is where it takes the password from me, which might be too long. That is in line 8. So I want to put a breakpoint at line 9 because I want to stop and see what happened after line 8. So let's break at 9. All right. Now I'm going to run, and I'm going to put in a normal password that's not too long. So run, give it a password that's not too long, and now I can see what's happened. I can look in the registers with info registers, and you'll see the stack starts at 5D0 and it goes to 5E8. It's not a very big stack because I don't have a lot of variables in this subroutine, so I can examine the stack, examine 12 32-bit words starting at ESP here. And let me make my window wider again and run that again to make it look, all right, a little bit more wider. All right. So this is what's on the stack. And you see there's some other things, and here's my capital A's. A capital A is 41, so there's some of my A's, here's more of my A's, and there's more of my A's. Then I hit the end of the stack, which is EBP 5E8. So this is 5D0, 5E0, 5E4. This is the word starting at 5E8. Right after that comes the return pointer. This is the address that the code will move to when it's done processing this routine. So if I stomp that and make that an invalid value, it will crash. And as you can see, that did not happen here because my string wasn't long enough. So that's the point. All right. And so I can overflow it with this longer injection. So if I run it again, and I say, yes, just quit this run, I want to run it again. And I put in that long password. And now I look at info registers. I'll just look right on the stack. Now you see I have AA, BB, BB, 42 is B, 43 is C, and on you go. And if I do info registers to see where the stack is, it should be in the same place, ending at 5E8. So that is here. This is the end of the stack. That is the return pointer. So that is A, B, C, D, E, F, G, G, H, H. The last two G's and the first two H's ended up in the stack pointer. It ended up in the return pointer. So I now control the return pointer. And so if I continue until it crashes, it's going to crash. And here it's telling me the instruction pointer contained this invalid value, which is FFGG. And if I do info registers, I can see that. Info. That is in fact in the instruction pointer. Some other things got corrupted too, like EBP and EBX, but the only thing I really care about is EIP. So I can now inject anything I want into the instruction pointer. And in order to win, I just have to find the win command. So I can do that with disassemble. If I disassemble the win function, it'll tell me where it is. So there's the win function. 17, 62, 55, 56 are the bytes I need to send. So I'm going to have to send those from Python. So I'm going to copy this. That's my target. And now I'm going to make a simple Python script. So I will quit the debugger and nano exploit 32.py. And I'm going to put in that value. That's my target. Okay. And now I'm going to put in this code here. All right. And I'm going to take that value and put it up here instead because my example value is not the one that works on this system. So it's that one. All right. So here I go. I put in the A, B, C, D, E, the first two Fs, and the FFGG has to be replaced by the bytes in this address. And you have to put them in backwards because Intel is little endian and strings are put in order. So it's one of the things you get used to. So I have to put in 17, 62, 55, 56. So let's do that. This is 17 and this is 52 and 55, 56. That should work. Let's see if it works. So if I run that, let's chmod plus X, my example 32. Now I can run it. Okay, and it prints out this junk. And in this case, the injection, I have FF, then I have, so some of those characters are in fact printable, one isn't. This is, but that's fine. So now I just need to take that and feed that into my a file to work with. So I'll call that attack 32. And now if I do ls minus L, my attack 32 contains 41 characters, which is what I expect. And now I can test it in the debugger. So if I run this thing in the debugger, I called my file A32. I can put a break at 9 again. And then I can run --args. And it is this less than the file I made, which was A32. So instead of taking the password from my command line, it'll read it from that file. And that way I can put unprintable characters in it. So now I run it, it hits the breakpoint. I can now do info registers and see that the stack starts at 5D0 and it goes to 5E8 again. So I can examine the stack. And now it has this address, 5655, 5217. Let's check that by disassembling when. So that number, 56, 55, 62, 17, I got 52 instead of 62, so it's going to crash. If I continue, it crashes because that's a mistake. So let's go fix that. Quit. Yes, quit anyway. It was 52. Yep, I wanted 62, but I put in 52. You can't do that. 62. All right, this one might work. Let's go back into the debugger and put in the breakpoint, run with arguments. All right. And, oh, it's a different file name I used. I just called it A32. There we go. So now it hits the breakpoint. Now I can do info registers and see that the base pointer is at 5E8. And if I examine the stack and look at that word, this is the end, that's the stack frame, and the next byte is this address, 56, 55, 52, 17. Oh, did it again. I changed my script, but I didn't run the script to put it in that file. So my script is EX32, and the file I need is A32. All right, now I should be able to do it. I go into the debugger, and I should be able to make the breakpoint and take the data from here. And now if I do info registers, I see that the base pointer is still at 5E8. And if I look at what's on the stack, it is this number, 56, 55, 62, 17. And if I disassemble win, that is the right number this time. So if I continue, it prints you win. Then it crashes because I had some collateral damage. I changed the base pointer and other pointers and did not fix them. So, but I did gain control of the instruction pointer, and I was able to make the code go to a place that the developer didn't want it to go. So this is the fundamental basic buffer overflow, and all of your memory corruptions are based on this. And you can practice it, and you can even practice it without having a Linux machine, because if you go down here, I made a server, and the server is running GDB. So you can practice exploiting this server. And I think that's the first one right here. Okay, so here, for example, I can take a string. So if I put in AAAA and then debug it, it will show me the source code. And you see the source code has a couple flags in it. So your goal is to redirect execution to these parts of the code, and then it will print out the flag. These X's are, of course, substitute there instead of the flag. And the main function asks you for a product key and reads it into a variable 100 bytes long, but it doesn't restrict the length. So you can cause an overflow, but causing an overflow in main is actually not a very good idea because it's hard to exploit. What's easier is to make an overflow in a subroutine. So it copies that into a thing only 25 long. So the way to exploit this without making your life too difficult is put in injections that are less than 100, but more than 25. And so the first thing you have to do is make the 30th byte equal 7. And the next thing you have to do is redirect execution to this win routine. And it runs the debugger commands here for you. So you can see the stack in that function, the vulnerable function, and you can see that the stack ends at C48. And you can examine the contents of the stack here. So this is the unmodified pointer. And the way to exploit this, you can use the form, but there's no real need to. The parameter is right there in the URL. So what I would do, and the way I usually do it, is I just modify this URL. So I've got AAAA. And so if I want to now see it crash, I'm going to do this. I'm going to make this much longer, like that, for example. And now if I resolve that, just go to that location. What did I do? Oh, I didn't kill the old one. Delete, paste, there. Now I've entered a long product key, and it crashed with a segmentation fault, and the instruction pointer is AAAA. So that was enough. Here's all the A's I injected, and that was enough to hit the return pointer, which you can see because EBP is here at C48. And C48 is there. So this is the stack frame, and that's the return pointer. So some of my A's hit the return pointer. So by just modifying the data here, I can send anything I want. And if you want to send a non-printable character in a URL, you do it this way. Let me bring up this. To send a non-printable character, you use %. So I could put %04 here, for example, and that will be interpreted as 1 byte of 4. So let's send a few of those. All right. Now, if I go to that URL, delete the old stuff, and put in the new stuff, now I've injected a string, and you can see that I've got 41s for a while, and then I've got some 04s. So you can inject any binary stuff you want by using that syntax, % and 2 characters for the hexadecimal. So you can practice your buffer overflows here without installing anything, and you can do it in 32 and 64-bit. So actually, I say this one project is probably the most important one in the whole course. This is where you practice exploiting simple buffer overflows, and it's good for you.